that would be our function. And if you plug that into your grapher, let's bring out the graphing calculator. We'll type y equals 2 and the square root of 10.24, and we'll raise that, and this is where you need your caret button, to the x. And I'll adjust my window accordingly so that I can see around those 2 points. So I want to be able to see below and to the left of 0, 2, so I could go over to maybe -3 for the x-min and maybe -5 or -10 for the y-min. Just anything below the x-axis would be good. Then I want to be able to see to the right of 2 and above 20.48, so maybe I'll go over to 3 and up to 25. Alright, that should be a good viewing window. If you have your standard zoom, you can tell that the graph looks like an exponential, but it's a little hard to see the points that we're interested in. Alright, so our graph looks pretty solid. Let me go to the table and verify that the points that are supposed to lie on this graph actually do. So if I go to the table, my table is currently set up for auto with a starting point at 0 and a step every unit. So if we plug in 0, we see we get 2, so the point 0, 2 is good. And if we come down to x equals 2, we see that the output is 20.48. So that second point lies on the graph, and that is all that we were asked to accomplish. So our graph does what we want it to do. It's an exponential function, and that is all that we need. So the next topic is the exponential growth or decay model, which is sort of a generalization of what we've already seen. And that looks something like P of t, where P represents our population or our amount or the value of whatever it is that we're measuring, and T rather intuitively represents time. So the setup looks a lot like what we've already seen. We have P sub 0, which is a constant multiplier of the basic exponential part of this function. So that P sub 0 represents our initial amount, our initial value. And the reason for that is if we plug in 0, in other words, if time is 0, if we're just starting out, then we get P sub 0 times b to the 0, and that gives us P sub 0 times 1, which is itself P sub 0. In other words, the y-intercept, or the vertical intercept, of this sort of general model is 0, P naught, P sub 0. We call B, instead of calling it the base, we call this the growth or decay factor. The reason for that is that's what we're multiplying by each time we increment t. So if we're doubling, our growth factor would be 2. If we're tripling, our growth factor would be 3. If we're decaying, if we're getting half as much value for every increase in t, then this would be a decay model, and we would call it the decay factor, and b would be 1/2. So it's a growth model if b is greater than 1. It's a decay model if b is less than 1. And that kind of makes sense. If b is less than 1, our function would be decreasing and our graph would be falling. If b is greater than 1, then our function would be increasing and our graph would be rising. So let's take a look at one of these in action. Suppose we have a data set here representing a population or an amount over time. Here we're letting time be represented by x, or maybe x doesn't represent time. This is some other type of exponential situation. So the first thing we would like to do is determine, is this going to be a growth or decay model? So I would note that when we first start out, our amount is 34, and later, after 3 weeks or months or minutes or whatever x represents, our value has decreased down to less than 1, down to 0.87. So I would argue that this is a decay model. In other words, we know now that b is going to be less than 1. Now another easy datum to pick out from this information, from the table that we are given, is the initial value. Remember, the initial value is however much we have at time 0. So the initial value, p sub 0, is going to be 34. So we're on our way to being able to figure out the formula for this situation. To do that, we're going to need to figure out exactly how much our amount is growing or decaying every time period. So, what do we know so far? We know that p of x is going to look something like p sub 0 times b to the x, and we already know what p sub 0 is. Let's instead write this as p of x equals 34 times b to the x. Well then, if we plug 3 in for x, we would get 34 times b cubed, and that's supposed to be equal to 0.87. So we'll enforce that based on the second point that we're given, and then we can solve for b. So if I divide both sides by 34, I'll get b cubed equals 0.87 over 34. Now you can plug that into your calculator. I'm going to leave it exact for now, because now I'm going to cube root both sides to get b equals the cube root of 0.87 over 34. Now I'll plug that into the calculator and round to, let's say, 3 decimal places. And I am coming up with approximately 0.294. Let's see. Let's round that up to 0.295. So b, in this case a decay factor, is 0.295. And now coming up with the function is basically done. We just supply all of the defining components. We have our initial value, 34, and our base, our decay factor in this case, 0.295, to the x. So now that we've got our function, we can very easily plug that into the graphing calculator and use the table setting to calculate the rest of those outputs based on the inputs of 1, 2, 4, and 5. Alright, so if I type in 34 times 0.295 to the x, and I go to the table settings, I'd like to make sure that the table is set to auto this time, which mine currently is, and the reason for that is if I start at 0 and I have the calculator generate 1, 2, 3, 4, 5 for x, then I can just read down the right-hand column. So for x equals 0, y equals 34, check. For x equals 1, we get 10.03. Now, if we want 3 decimal places of accuracy, we might want to scroll over and see if that's as accurate as it gets, and 10.03 seems to be it. Then for x equals 2, we would get 2.959. And for x equals 3, we get 0.87. It's a little bit off, but that's because we rounded here our base. So if we plug in 4, we get 0.257. And if we plug in 5, we get 0.076. So there's our table completed. We couldn't have done that without the function. Now, so far we have only really examined the situation where we know by what factor our amount is increasing. So we could say that something is doubling every year, or tripling, or increasing by a factor of 1.2 if it gets multiplied by 1.2 every year. But the other way we can express changes in amounts is by saying how much they increase. So right at the bottom of that page, definition 6.3 discusses the growth or decay rate. So far we've seen growth and decay factors, but in this situation, for example, in the question that we are looking at, we have an amount in a bank account, and we're told that it increases by 4% every year. We're not being told the factor, we're being told a rate of increase. So referring to that definition, if we think about how much money is going to be in the account after a year, in 2010, we're going to have 1,000 and 4% on top of that. So the way that we would describe the growth factor, B, that's going to be 1 plus our growth rate, R, where R is 4%. In other words, 0.04. So we always need to convert from percent into usable numbers, decimals. Alright, so we can conclude that B is going to be 1.04. That's the factor by which our money is being multiplied to determine how much will be left after a year. So after a year, we'll have $1,040. After 2 years, we're going to multiply 1,040 by 1.04, and that'll tell us how much we have in the account. So the other piece of the puzzle, our initial amount, the amount at time 0 is 1,000. So remember, 2009 is sort of our starting point. So 2009 is time 0. So our population function, or our exponential growth model, P of t, tells us how much money is in the account. We'll have 1,000 to start, and we're multiplying that by 1.04 every year. Okay? So if we do this once, our exponent would be 1, and we would multiply 1,000 by 1.04. If our exponent is 2, we'll multiply 1,000 by 1.04, and then we'll do it again to determine how much money is left after 2 years. Alright, so that is our setup when we are given the rate of increase. Now, if this were a rate of decrease, then our decay factor would have to be, is going to look a little bit different. So if we have a rate decrease, if we're losing money, then B is 1 minus R. In this case, where R still equals 4%, but this time we're losing 4%. So we have the 1 there to account for the money that we have, and then we're knocking off 4%, leaving us with 1 minus 0.04, or 0.96. In other words, we'll have 96% of our money because we're losing 4% of our money. So our model would look a little bit different. P of t would then be 1,000 times 0.96 to the t. And notice this would be decaying because b is less than 1. And that makes sense. If we're losing money, we should have a decaying function. Here, our b is greater than 1, and that reflects the growth taking place in the bank account. Now, the final strange topic in this section is that of changing time frames. So suppose here we have a colony of bacteria, and we begin with 60 organisms, so P sub 0 would be 60. We notice that the population quadruples every 2 weeks. But that might not be useful for us. Maybe we want to know about what's going to happen after week 3. Well, then knowing 2-week increments isn't as helpful. So what we might want to do is recognize what our base is going to be. Our base here, we're told that this population quadruples, so we're going to have a growth factor of 4. So I can begin setting up our equation. P of t is going to have the initial population times the base. Now we're going to be raising to a power. And, our base was actually 4. Let's put that in. So we're supposed to be raising to a power in such a way that 2 weeks in, we multiply by 4. 4 weeks in, we would multiply by 4 and then multiply by 4 again. So our exponent after 4 weeks should be 2. So I like to think of this as 2 separate quantities. What is our exponent going to be, and what is our time frame? Well, after 2 weeks, our exponent should be 1, right? That's 1 time frame. After 4 weeks, our exponent should be 2, right? We want to multiply by 4 twice, so we want to multiply by 16. After 6 weeks, our exponent should be 3. That's the 3rd time we check in. So what's the relationship here? Well, the exponent is going to be half the number of weeks. So if t represents the number of weeks, then our exponent should be t over 2. Right? After 1 week, our exponent should be a half. After 3 weeks, our exponent should be 3 halves. Right? And this, if this is t, then this is t over 2. Alright, well, let's see if this works. So our population after 0 weeks should be 60. So 60 times 4 to the 0 over 2. That's 60 times 4 to the 0. That's 60 times 1, which is 60, so we're good. Okay, our population is supposed to quadruple after 2 weeks, so we should have 4 times the original 60 after 2 weeks. So if we look at P of 2, that would be 60 times 4 to the 2 over 2. We'll simplify that exponent. That's 60 times 4 to the first, which is 60 times 4, which is 240. Exactly quadruple the original 60. Excellent. So it looks like we're in good shape, which means we could use this function to figure out how many bacteria there are after 5 weeks. That would be 60 times 4 to the 5 halves. That's something I would probably go ahead and plug into the calculator. So let's see what that works out to. If I type in 60, and I multiply that by 4 raised to the 5 halves, I get approximately 1920. Actually, it's not approximate, that's an exact number. So that's how many bacteria are in our population, or in our colony, after 5 weeks. So that's how you would handle the time frame. I like to think of what is my variable, and how is that related to the exponent, based on the situation that we were given in the setup. Alright, well, that is all of the different topics out of this section. Go ahead and get started on those homework problems. Feel free to shoot me and ask your teacher, and bring any questions that you still have to class when we meet again.